A student prepared solutions of sodium chloride and glucose separately by mixing one formula weight of each in 100 ml of water. However, he forgets to label them. In order to identify the solutions, what he did was that he tried to calculate the molecular weight using the method of colligative property. To his surprise, one solution gave the molecular weight of glucose as expected. However, the molecular weight observed for the other one, that is for sodium chloride solution, was less than that of true value. Do you know why an abnormal molecular weight is observed with sodium chloride solution? In this video, we will discuss the reason behind the abnormal molar mass and the method to be adopted to account for this deviation. First of all, let's consider the dissolution of 1 mole of potassium chloride in water. Here, the resulting solution will contain both potassium ions and chloride ions. That is, there would be 2 moles of particles in the solution. 1 mole of potassium ions and 1 mole of chloride ions. As discussed before, the colligative properties depend only on the number of solute particles. Here, in potassium chloride solution, the number of particles is doubled. Hence, the observed colligative properties also will be double than that of calculated one theoretically. This means if there is dissociation of solute particles, the measured colligative properties such as osmotic pressure, elevation of boiling point, depression of freezing point, etc. will be much higher than that of calculated on the basis of undissociated molecules. Further, as molar mass is inversely related to colligative property, when there is dissociation solute into ions, the experimentally determined molar mass will be always lower than the true value. For potassium chloride, as the number of particles becomes double, the experimental molar mass will be half the expected value. Now let us discuss organic molecules in which there will be association of molecules. For example, in the case of acetic acid. Acetic acid dimerizes in benzene via hydrogen bonding. Thus, there is decrease in the number of particles. Consequently, the calculated values of colligative properties will be half and the experimental molar mass will be twice than that of true value. Such molar masses, that is, either lower or higher than the normal value, is called abnormal molar mass. Upon dissociation of solute particles, the experimentally determined molar mass is always lower than that of the theoretically calculated one. And in contrary, in the case of association of solute molecules, the theoretically calculated molar mass would be less than that of the experimentally calculated molar mass. To account for the extent of dissociation or association, Van Hoff introduced a factor I known as Van Hoff factor. Van Hoff factor is a ratio of observed colligative property to that of calculated value. For association, I is considered less than 1 and for dissociation, it is considered greater than 1. Next, we will see how the equations for the calculation of colligative properties are modified by incorporating Van Hoff factor. The relative lowering of vapor pressure, that is P10 minus P1 divided by P10 equals I into N2 by N1, where I is the Van Hoff factor and N1 and N2 are the number of moles of solvent and solutes respectively. Similarly, we can have equations for elevation of boiling point, depression of freezing point and osmotic pressure. Here, Kb is the ebullioscopy constant, Kf cryoscopy constant, M the molar mass, T the temperature and V the volume of the solution. Now let us try to answer the question which I have asked you in the beginning. When one formula weight each of sodium chloride and glucose was dissolved separately in 100 ml of water, the true molecular weight was not experimentally obtained with sodium chloride solution. This was because dissolution of each formula weight of sodium chloride in water produces 2 sodium ions and 2 chloride ions, that is 2 particles, whereas the glucose can give only 1 particle for each formula weight. Hence, as discussed earlier, the colligative properties of sodium chloride solution would be double and the molar mass will be half when compared to theoretical value. Now let us summarize what we have learned today.
Manorama Horizon. Learning made simple.